Materials having a bandgap do not follow the Lorentz or other previously presented models well. These materials are typically semiconductors with bandgap. They have negligible loss below the bandgap and have very clear transition to high loss within the bandgap. Here are two examples of such materials. These graphs show transmission of light through a wafer of some specific thickness. First, let's take a look at zinc selenide. It has a bandgap at around 480 nanometers. Loss is small at longer wavelengths, since the transmission is large. Loss is high at short wavelengths above the bandgap. Secondly, we have titanium dioxide, whose crystal structure in this case is rutile. It has a bandgap at very short wavelength of around 350 nanometers. Loss is very small at visible wavelength range, and light is absorbed at ultraviolet wavelengths. Due to rapid change of loss near the bandgap, none of the variants of the Lorentz model are appropriate for these materials. However, one suitable model is called a Tauck Lorentz model. In semiconductor technology, it's common to use energies, meaning that E is photon energy and Eg is the bandgap energy. Compared with the Lorentz model, we use a more modern model of a material based on valence and conduction bands for electrons. At photon energies that are higher than the bandgap, electrons move from a valence to conduction band. It means that at smaller energies and longer wavelengths, the material is transparent. When energy is increasing and wavelength is shortening, the material starts to absorb due to transitions from the valence to conduction band. This transition is modeled by a Tauck function, which is 0 below the bandgap and increasing above the bandgap. To derive a Tauck Lorentz model is the classical Lorentz model separated to its real and imaginary parts. The imaginary part is modified by multiplying with a Tauck function. It is then describing lossless material below the bandgap, but at losses above it. To get the complete permittivity function, we also need the real part. In this case, the real part is not simply a real part of the Lorentz model, but it needs to be evaluated from the imaginary part using the Kramers-Kronig relations. The good news is that this evaluation can be done analytically. The bad news is that it can be only performed for certain Tauck functions, and the result is really complicated. This function is anyway given as a MATLAB script in the lecture notes. Finally, we'll see an example of permittivity and refractive index following the Tauck Lorentz model. Below the bandgap, the imaginary part is zero, and above it, it's rising rapidly. Basically, the material is lossless at long wavelengths, but the losses are increasing towards the short wavelengths or ultraviolet wavelengths. This model is suitable for various materials with more or less clear band gap, which include amorphous silicon and titanium dioxide.